Today we're going to continue on with our look at machine learning with an introduction to dimensionality reduction. So why do we need dimensionality reduction? Let's say you have 1,000 variables in your data set. It's a massive data set width-wise, maybe not length-wise, but how do you visualize or process that? How do you find correlations when you have so many variables and you don't know what's important and what's not? Dimensionality reduction finds a simpler representation of the data with fewer variables that still captures the most important structure or pattern. It makes data easier to visualize and interpret, speeds up computation, reduces noise, and helps with overfitting in models. The key idea is asking, can we rotate and project the data onto a simpler shape? And that's where singular value decomposition comes in. Singular value decomposition is like eigendecomposition, but the main difference is it works with non-square matrices. SVD is a matrix factorization technique that expresses any real matrix as a function of U, sigma, and V transpose. So decomposition breaks A into three components: an orthogonal matrix, left singular matrix, a diagonal matrix with non-negative real numbers, and an orthogonal right singular matrix. Again, very similar to eigendecomposition. In fact, it's the same for square matrices. SVD generalizes the idea of diagonalization in non-square or singular matrices. SVD reveals intrinsic structure of the matrix with applications for dimensionality reduction, principal component analysis, and noise reduction, signal compression. So geometric interpretation should be considered rotation, scaling, and rotation. So here we go from our original matrix, and then we stretch it in each of the directions of greatest variance. So we're transforming a unit circle into an ellipse. So let's go through a step-by-step example with this matrix A. We'll find the singular value decomposition of the matrix using the eigendecomposition of A transpose and A transpose A, singular values, square roots of the eigenvectors, eigenvalues, columns of V, eigenvectors of A transpose A, and columns of U derived via UI equals 1 over sigma I A VI. So we start out by finding the eigenvalues of A transpose A. So we're going to do matrix multiplication, this times this, 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 this times this. 17, 8, 8, 17. Then we're going to take the determinant, so A transpose A minus lambda I, 17 minus lambda, 8, 17 minus lambda, 17 minus lambda squared minus 64. The roots of that are 25 and 9, so the singular values are 5 and 3. We find the unit length vector in the kernel of matrix A transpose A minus sigma squared I. So here we're going to find A transpose A minus 25I, and this row reduces to 1, negative 1, 1, and the unit length vector in this kernel is 1 over root 2 to 1 over root 2. So now that's the V1, and then V2 is we find the unit length vector with the next eigenvalue. So A transpose A minus 9I. This reduces to 1, 1, 1/4, negative 1/4. The unit length vector in this kernel is 1 over square root 18, negative 1 over square root 18, and 4 over square root 18. And the final vector can be found by computing the kernel of A transpose A, or by finding a unit length vector perpendicular to V1 with transpose perpendicular to V2. There we go. And then now we compute the left singular vector, which is just the matrix that outputs A when multiplied by sigma and V transpose. Or we can also do sigma UI equals A VI, or UI equals 1 over sigma A VI. So that leaves us with this set of matrices, this singular decomposition. And so we have our final decomposition where we have our U, we have our sigma, and we have our V. Notice that they don't necessarily have to be of the same dimensions. In fact, they often are with quite non-square matrices. Each component captures specific parts of the transformation. V captures the input dimensions. Sigma is how much to scale along each direction. And U is the output dimensions. Key takeaways: SVD applies to any matrix, not just square ones. It decompresses the matrix through rotation, scaling, and rotation, reveals the rank, null space, and range of the matrix, and forms a mathematical foundation of PCA and other techniques. PCA is one of the most widely used dimensionality reduction techniques. It transforms data into a new set of variables that captures the maximum variance. Mathematically, PCA can be derived using SVD on the centered data matrix. So the steps: you standardize the data, you compute the covariance matrix, perform eigendecomposition or SVD, and select the top eigenvectors from the covariance matrix. So standardized data, you subtract the column mean from the original data and divide by the column standard deviation for all of the columns. This ensures that variables with larger scales don't dominate the result. You take the covariance matrix, which captures how variables vary together. You perform eigendecomposition of the covariance matrix. You sort the eigenvectors by their corresponding eigenvalues. Eigenvectors with the highest eigenvalues capture the most variance, and for non-square matrices, you can use SVD. So you have correlated high-dimensional data. You center the points. You compute the covariance matrix. You take the eigenvectors and eigenvalues. You pick the eigenvectors with the highest eigenvalues. You project the data on those eigenvectors. And then you have uncorrelated low-dimensional data. PCA and regression. PCA regression uses principal components instead of the original variables. It helps reduce multicollinearity and overfitting. And it's useful when predictors are high-dimensional or highly correlated. But to interpret the predictors, you have to convert back to the original feature space. So there's the first dimension and the second dimension. Unlike PCA, which is unsupervised, LDA is supervised dimensionality reduction technique. PCA finds directions that maximize the overall variance, while LDA finds direction that maximize class separability. LDA is often used in classification tasks such as face recognition and topic modeling. And here we go. Here is a visualization of LDA. And that's our introduction to dimensionality reduction. Thank you. Hope you have a great day.